Hi, my name is Danilo Krasi, and today we'll discuss a paper called Neural Preset for Color Style Transfer. It's not rocket science like another version of ChatGPT or some single frame reconstruction using your grandpa Nokia, but it's still a pretty interesting topic, especially if you want good Instagram photos. A lot of people spend hours styling their feed to make their page look authentic. Or maybe your cowboy meme video needs some dollars trilogy vibes. Or you're a Danny Villeneuve fan and you decided to add some Blade Runner vibes to your cat video. Or maybe you once tried to replace the sky in a video, and transferring the style of the new background is a painful topic for you. So if any of this is true, then you are interested in style transfer instruments. Basically, there are three types of such techniques. The first one is color style presets, such as image filters or lookup tables. Even though these presets are widely used and show good results, these filters or tables are manually created with predefined parameters, and they are not able to generate consistent color styles for images with diverse appearance. The second technique is statistics-based methods. Earlier color style transfer methods, they focus on retouching the input image according to low-level features like variance or mean of images, or the histograms of filter responses. They disregard high-level information, resulting in artifacts and unexpected changes in image inherent colors. And the third techniques, the third type is deep learning-based models. Although they give promising results, they typically suffer from three limitations. They can also produce unrealistic artifacts because these types of methods perform color mapping based on convolutional models, which operates on image patches and may have inconsistent outputs for pixels with the same value. The second limitation is that they cannot handle high resolution images due to their huge runtime memory footprint. And the third limitation is that they are inefficient in switching color styles because they carry out color style transfer as a single stage process, requiring to run the whole model every time. So what did the authors presented in neural preset algorithm? They basically presented two main features. The first one is deterministic neural color mapping module. Filters and lookup tables avoid artifacts, but they are handcrafted. CNNs can automatically map the color style from a well-retouched image to another, but usually lead to artifacts, slow speed, and high memory consumption. So the authors proposed the NCMs that takes best features from methods above, but has only a few hundred learnable parameters and can model arbitrary deterministic color mappings. And to train the model, the authors used self-supervised learning strategy, custom self-supervised learning strategy, since it's expensive to annotate ground truths for color style transfer. Most methods either minimize perceptual losses or match the statistics of image features. However, such weak constraints usually result in severe visual artifacts. And the authors presented a new SSL strategy for neural preset, which not only learns from reconstructing perturbed images, but also enables the trained models to transfer color styles between arbitrary images. So let's speak about the NCM more in details. So the algorithm is next. We give an image I with size HW3. We downsample it to thumbnail I had, then feed it into encoder E and obtain image adaptive color map and matrix T, resize or reshape this matrix to two-dimensional matrix TKK. Parallel, we unfold I as a 2D matrix of size H times W3, embed each pixel in I into a k-dimensional vector by a projection matrix P, multiply the embedded vectors by T, and finally apply another projection matrix Q to convert the embedded vectors back to RGB color space and reshape pixels to output Y with new colors. So here is the neural preset pipeline. The authors designed an explicit two-stage pipeline based on the NCM model. The key insight behind the pipeline is that if we can separate the color style of an image from its content, so we can effectively transfer different color styles to the image content. Since we need to alter the image color style but preserve the image content, the authors propose to utilize a pair of DNCMs named NDNCM and SDNCM. While NDNCM converts the input image to some space that contains only its content, SDNCM transfer this content on some target color style using parameters extracted from the style images. So how to represent the image content? The authors proposed to learn a normalized color style space representing the image content by backpropagation. In such a normalized color style space, images of the same content but with different color styles should have a consistent appearance that is the same normalized color style. As shown on the figure on the slide, the authors modified the encoder E to output parameters D and R, which are applied as the parameters of NDNCM and SDNCM respectively. Suppose that we want to transfer the color style of image IS to the image IC. So in the first stage, we convert IC to normalized space ZC using NDNCM. And in the second stage, we extract parameters RS, and using SDNCM, we combine normalized image IC, ZC, with those parameters and get some stylish new image YS. And besides, the design of the pipeline supports fast style switching. In the stage C, the preset color style parameters R1 and R2 can be reused by SDNCM to stylize ZC to obtain Y1 and Y2. And about self-supervised training strategy, the authors developed a self-supervised strategy to train neural preset, as shown in the figure. since no ground truth stylized images are available, they created pseudo stylized images from the input image I. So they add some random perturbation to image I to obtain two augmented images I, and I-J. As a perturbation, they used some simple operations that change only image colors, like filters or lookup tables. So the first stage of the pipeline, it aims to normalize the color style of input images, which means that input images with the same content but different color style should be consistent in the normalized color style space. Hence, the authors applied L2 consistency laws between the outputs of the stage, and formally they predicted the NCM parameters di, dj to transfer iij to zi, zj, which are constrained by the laws below. And the second stage of the pipeline aims to stylize the normalized images. So to convert the input images to new styles, the authors swapped the predicted SDNCM parameters R to stylize the two samples. That means that Zi will be stylized by Rj and Zj by Ri. And the authors applied L1 reconstruction laws between I and Y to learn color style transfer. As in the formula, and the final loss, it's just a combination of two losses, as in the formula on the slide, where lambda is controllable weight. Let's speak about metrics. Experiment setup. They used images from Coca dataset. The author also used about 5,000 lookup tables files. Along with the random image filter adjustment strategy as input color perturbation during training. They collected 50 images with diverse color styles and pair each two of them to build a validation set consisting of 2.5 thousand samples. And about implementation, as encoder, the authors adopted efficient net model. They fixed the input size of encoder to 156 to 156, set the parameter dimension k in the NCM to 16, train neural preset by Adam optimizer for 32 epochs with a batch size of 24. And the initial learning rate is 3e minus 4, and then it's multiplied by 0.1 after 24 epochs. And the lambda was set to 10. So about metrics, there are basically three metrics. The first one, it's user study. The authors invited 58 users and asked them to rank results of different color transfer models. They compared their model to some open source deep learning based model, and also some classic statistic based model named CT on the slide. So, of course, neural preset was the best. The authors usually rank it to the top 3. And hooray, hooray. And the other two metrics was content similarity and style similarity. For color style similarity, the authors trained the discriminator model on annotated dataset, and for content similarity, they used lightweight dense CNN for edge detection and calculate the content similarity just as using structured similarity metrics on edges from lightweight dense CNN. So again, neural preset was the closest to ideal model. Hooray. And about the efficiency and memory consumption, the fact that neural preset process each pixel independently, it's not consume a lot of GPU memory. So you can see that the consumption is the lowest compared to another models. And also neural preset works pretty fast. So you can, the authors achieved 56 FPS on a 4K video, which is pretty cool too. And finally, some images comparisons. Here you can see the results of some models. On the first column, there's input images. On the second column, some style images. On the third column, results of neural preset. Again, it looks pretty nice compared to another methods. To be honest, I can't see any difference between input images and deep preset. Maybe the authors forgot to pass deep preset results and just leave the input images. I don't know. Still looks pretty nice. About limitations, neural preset has three limitations. The first one, you can see that if the input image has a high compression ratio, God bless JPEGs, that artifacts may appear on the photo. Also, results may be unsatisfactory if some colors in the input images, for example, green color here, if these colors not exist in the style images, then results may be not so good. And the third limitation is that neural preset method fails to map blue, sky, or water in an image to different colors separately, although prior methods may handle blue, sky, or water separately. They typically cause heavy artifacts. So, and as you understood from introduction, I had a project with sky replacement, and to achieve the best speed of the pipeline, I used classical statistics-based approach, and sometimes results were not as good as I wanted. So I decided to compare those results with a neural preset. Here you can see a cow on Tatooine, with style of Tatooine, and statistic-based approach returns quite acidic colors. It lost a lot of details on the cow, while neural preset looks much more pleasant. Here is another example: cow and some space background. The results are pretty good in both methods. It's hard to say which of them did a better job. And the third example, it's some dogs with another space image. Again, the results are quite similar, but I guess for me, a neural preset looks better because again, the colors are less acidic, so I would prefer neural preset. And conclusions, the authors proposed a simple but effective neural preset technique for color style transfer. The method is based on two core designs. It's the NCM module and a two-stage pipeline that divides the task into color normalization and stylization. And due to the unavailability of pairwise datasets, the authors trained neural preset via self-supervised strategy.